These are the square numbers. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. If you add up all of the square numbers starting from 1 times 1 and ending anywhere, here I have 9 times 9, you may have heard of a nice formula that finds the sum. I want to find out why this formula is true. Now, the way that you usually learn about this is you learn that the formula, when you add from 1 squared to n squared, is something, and the formula is written on the screen for you to look at. I want to use a different method. Let's see if we can find the formula by doing some algebra. This way of doing algebra will look a little bit strange because I'm going to use cubes. 0 plus 1 cubed. Now, you might say this is very easy. This is just 1 cubed, which is 1. But I want to do this in a very strange algebra way that will let me find the sum of the squares. You see, when I have something plus something cubed, well, that is 0 plus 1, 0 plus 1, 0 plus 1. And if I expand the brackets, expanding the brackets means from each of the brackets choose one of them. Well, of course, you'll have 0 times 0 times 0, but you'll also have some other kinds, 0 times 1 times 0, 1 times 0 times 0, and 0 times 0 times 1. And you'll have another set of them, which has two ones, 1 times 1 times 0, 1 times 0 times 1, and 0 times 1 times 1. And the last kind will be 1 times 1 times 1. I'm writing all of these out carefully so that you see that there is one kind with all zeros. There's one kind with all zeros. There's one kind with all ones. And there are three kinds with 2 or 1 ones. Well, we usually write that as an algebraic expression. You're used to maybe seeing x plus y cubed is equal to, there's x cubed, which happens 3 times, plus 3 times you'll have x squared y, plus 3 times you'll have xy squared, and then you'll have the y cubed. So I showed this in 2 ways. The first was with just numbers, because I'm not sure what the different audience is watching this video. And so even if you're not so familiar with the x and y, you can see it through the numbers. X and y just let us say it doesn't matter that it was 0 and 1. Maybe these were just the 2 letters O and L. OK. Well, if I do this, I have this way of expanding x plus y cubed. I will use that for 0, 1. So again, I'll go 1, 3, 3, 1. Let me write it this way. 0 plus 1 cubed equals 0 cubed, that was all 3 zeros, plus 3 times 0 squared times 1, that was with 2 zeros and a 1, plus 3 times 0 times 1 squared, that's with 2 ones, and then plus, well, 1 cubed. I'll still write it as 1 cubed for now. That's 0 plus 1 cubed. I also will write 1 plus 1 cubed. What is this? Well, it's very similar. It's just that all the zeros become 1s. So it's 1 cubed plus 3 times 1 squared times 1 plus 3 times 1 times 1 squared plus 1 cubed. I'm going to do this many times. Let's do 2 plus 1 cubed. 2 cubed plus 3 times 2 squared times 1 plus 3 times 2 times 1 squared plus 1 cubed. And to see the pattern, I'm going to say I do this all the way to n plus 1 squared, cubed, n plus 1 cubed, and that will be n cubed plus 3 n squared times 1 plus 3 n times 1 squared plus 1 cubed. You may wonder why I'm doing this. Well, the reason I'm doing this is because I see the squares, 1 squared, 2 squared, up to n squared, are all in this column. I see some cubes here, but the same cubes are there. So if I add together all of the equations, on the left side, I have 1 cubed, 2 cubed, 3 cubed, up to n plus 1 cubed. Okay, I'm going to write that down because we're about to do some big canceling. The left side, now I will remember, 0 plus 1 cubed is 1 cubed. So I'll be doing 1 cubed plus 2 cubed plus dot, 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 plus n plus 1 cubed. These are the left side, equals. Now let's look column by column. This first column is 0 cubed to n cubed. Already I'm very happy. This and this have an enormous overlap. Many terms are on the same on both sides. What is this in the middle? I'll use red because it's what we want. The next piece is plus 3 times the sum of the squares, 0 squared, 1 squared, up to n squared. 0 squared is 0, so it's just the sum of the squares. 1 squared plus all the way to n squared. This I want to know. What's over here? Let's use green. This is, all the 1 squareds are 1. This is 3 times the sum of the numbers 1, 2, up to n. 3 times 1 plus all the way to n. This is something that many people learn much earlier in school. There's a nice formula for 1 plus 2 up to n. There are, of course, nice ways to prove that too, but for this class, I will assume you already know how to simplify this 1 up to n. Okay, we'll do that in the next piece. And the last one I want to put, 1 cubed plus 1 cubed, well, those are all 1s. And how many are there? There are n plus 1 of them there. Okay? So if I have n plus 1 of them there, it's just n plus 1. Okay. Now, it now becomes fun part. What is the canceling? The cubes are almost entirely gone. 0 cubed to n cubed will cancel everything else except the n plus 1 cubed, and all of this is gone. So now I will be able to say what this is in terms of all the rest. Let's call that x, because that's what I want to find. This piece is going to be x. So now I'm going to write on the next screen what we have left. N plus 1 cubed equals 3x plus 3 times this sum plus n plus 1. N plus 1 cubed equals 3x plus, it will be 3 times the sum of the numbers from 1 to n, which is n times n plus 1 over 2. There's a very nice way to prove this by a picture. If you haven't seen another class where I do this, or someone else does this, try it yourself. And then the last is plus n plus 1. This is nice. There are 2 ways to finish from here. One way is to multiply everything out and solve for x. Another way is to say, I see a lot of n plus 1s everywhere. I will factor that out. So let me move the x to this side. 3x equals. On the right-hand side, I will have a lot of n plus 1s. Well, this goes here. Well, what I mean is that we'll flip the equation. So I subtract on that side. Okay. So I'll have an n plus 1 times, here it's an n plus 1 whole thing squared. Again, what happened is I just flipped the equation because I want x on the left side. This is my n plus 1 cubed. I have to minus these because I move these to the left side. So minus 3 over 2n, that's this piece, because the n plus 1 is common, minus 1. Now we can expand this. This is not very painful to expand. So if I expand just this, let me focus on it with just this piece. N plus 1 whole thing squared. N squared plus 2n plus 1. Now minus the 3 over 2n and minus 1. Hey, this is quite nice. All of this together is n squared, and because I lined up the columns, it's very easy to subtract. 2 minus 3 over 2 is plus 1/2 n, and the plus 1 minus 1 cancels. We can simplify this by putting this over a common denominator with 2n squared plus n. And then it's easy to see that this factors very nicely as n times 2n plus 1 over 2. Putting everything together, this is then the formula that many people are familiar with. X, which is the sum of all of the squares from 1 squared all the way to n squared. Well, that is x, and that is multiply all of these divided by 3. Let me rearrange the multiplication so it's something that people are used to seeing. N times n plus 1 times 2n plus 1, all divided by 6. And now, you see, we have the formula not first, but last. Why am I showing you this way? If you know a formula because somebody told you, and then you prove it by using a method called mathematical induction, which is the usual way that you prove these things, you are only able to prove it if you already know what to prove. This is generally true in mathematics and in life. If you already know what you need to do, it's easier to do it. The hardest part is to know what to do. The reason I wanted to share this unusual way of finding the sum of the squares from 1 to n squared is that we never had to know what the formula was. It came out at the very end. There was a very creative piece in it, though, which I want to remind. And yes, I'm not saying that what I did is extremely easy to come up with. The interesting new idea was to not think about squares, but to go to cubes. That takes a leap of imagination, and this is not an easy proof to have. But why I want to emphasize this? You see, we took something that was simple, meaning only squares, and we made it complicated, meaning cubes. But somehow, by going from simple to complicated, that made the solution easier. This happens sometimes in math. Sometimes, when you can find the bigger picture where everything fits in, then it can help you find the smaller detail. And that is the sum of the squares from 1 to n squared.